Alrighty, welcome everybody to physics. This is going to be the first video in this Physics 1 series, and today we are going to start off with a review of the important concepts you're going to need to know for the upcoming problems. So, some things you're going to want to know before you continue this video is that the particle model represents a moving object as if all its mass were concentrated at a single point. So instead of drawing a detailed picture of a car accelerating from rest, for example, all I have to do is draw it as a dot. And if it's accelerating, then they move, the dots are more separated from each other. And it's like taking a snapshot at equal time intervals and concentrating your object of interest down into a dot like this. And it's just easier than, for example, like I said, drawing an entire car or a rocket or something like that. The next thing you're going to want to know is that position locates an object with respect to a chosen coordinate system, and change in position is called displacement. Velocity is the rate of change of the position vector r. Vectors are a topic we're going to explore later on, but right now you just need to know that velocity is the rate of change of the position vector r. You might recognize this from calculus when you did real-world applications and velocity was the derivative of the position function. And the next point you might also recognize from calculus, acceleration is the rate of change of the velocity vector v. You might recognize that from calculus as acceleration being the derivative of the velocity function, and these are just saying the same thing here. Rate of change is the slope, and the derivative is the instantaneous rate of change, or the instantaneous slope, or the slope at a single point. The next thing you're going to want to take into account is that an object has acceleration if it changes speed and or changes direction. So if you know those things, if you're comfortable with those ideas, then we can move on to the practice problems. If you're not yet there though, I suggest doing some more review, watching some other tutorial videos, and once you get comfortable with these ideas, then you can move on to the practice problems. Alright, so in this next question we are told that a car skids to a halt to avoid hitting an object in the road, and we are asked to draw a basic motion diagram of the car from the time the skid begins until the car stopped. And a motion diagram is different from a particle diagram because in a particle diagram I would condense this car down into a single point and draw it as a point. But in a motion diagram I'm just drawing the motion of the object, but I'm still drawing the object. It's not a point anymore. So I have this rough picture of a car I drew here, and it's on this graph right here, and this leftmost line represents where the skid starts. So right here is where the car starts to skid, and this end point, this end line right here on the right side, is going to be where the car stops. So this car starts skidding, and let's say I take a picture of the car at some equal time interval later. I can now say that let's say the car is over here. It's still moving, but it's starting to slow down, and then when I take another snapshot of the car, it's going to be closer to the second one because they're slowing down. So at equal time intervals, because the car is slowing down, each snapshot of the car will get closer and closer to the previous one. So then this one is going to be even closer. It's going to be right there. And then finally the car stops, and it's going to be basically overlapping or right next to the last picture of the car. And that's just how you do that one. So that's the first question done. Okay, so in this next problem we're told that we're watching a jet ski race, and a racer speeds up from rest to 70 miles per hour in just a few seconds, then continues at a constant speed, and we're asked to draw a basic motion diagram of the jet ski from 10 seconds before reaching top speed until 10 seconds afterward. So I've drawn this rudimentary time graph here, and I'm just going to say that the jet ski reaches top speed at 10 seconds, so 10 seconds before top speed would be time equals 0, and 10 seconds after would be 20. So I have this crudely drawn jet ski here. So if I put in another one to represent another jet ski, I can say that because it's speeding up, it's not going to be way out here. So I'm going to put it closer to like right there. And then it's still speeding up. So it's like right there. And now we can say that it's at t equals 10 seconds. It reaches top speed. So it will be going at a constant speed from now until 20 seconds, meaning that each additional jet ski should be at equally spaced time intervals to represent a constant speed if you're taking, let's say, a picture of the jet ski at equal time intervals. So I can do it like this, and I can say it's at top speed, so this next one needs to be at around an equal interval. So you can see that the distance between these two jet skis is basically the same as the distance between these two jet skis, and if they're not the same, I tried to make them the same. So then I can take that jet ski and I can say that t equals 20. It's like right there at another similar distance away from the previous one, and that represents speeding up, reaching a top speed, and moving constantly at that top speed until t equals 20. Alright, so in this next problem we're told that you drop a soccer ball from your third-story balcony, and we're asked to use the particle model to draw a motion diagram showing the ball's position and average velocity vectors from the time you release the ball until the instant it touches the ground. So this is what I have. So you can see that I've condensed the soccer ball into just a point, a dot, hence the name particle model. And I've got this y-axis here indicating that it's falling down rather than, it's falling vertically rather than horizontally. I've labeled this point here as the point of release, and this point here as the point of impact with the ball hitting the ground. And you can see I've got these velocity vectors here going down, and they keep getting longer, implying that the ball is speeding up as it falls, which implies that there's some sort of acceleration. And this is not taking into account terminal velocity, which is something we'll get to later in a different chapter. But this is just saying the ball is speeding up because gravity is acting on the ball and accelerating it further, into the ground. And then I've labeled my velocity vectors. I've got v sub 0, which is also pronounced v naught. I've got v sub 1, v sub 2, and v sub 3. And you can see I've got vector arrows, and these will always point to the right. Even if the ball is falling down or up or left, they will always point to the right. So that's your particle model there, and that's how you'd use a particle model to do this problem. Okay, so in this next one we're told that a softball player slides into second base, and we're asked to use the particle model to draw a motion diagram showing his position and his average velocity vectors from the time he begins to slide until he reaches the base. So this is what I have. So I've condensed the softball player into a single point so that I don't have to draw a softball player each time. And I've labeled where he begins to slide and where he reaches second base. And in between those, you can see that I draw velocity vectors kind of connecting one particle to another particle that's the same softball player just at a later point in time. So let's say if he begins his slide at t equals 0, this second point might be t equals 1, this third point might be t equals 2, and so on and so forth, just to illustrate the idea that these are equal time intervals, but you can see that he's slowing down because his velocity vectors are getting shorter and shorter, which means his acceleration vectors are pointing the other way, are pointing the opposite direction as his velocity vectors. And once again, I've labeled my velocity vectors v0 through v4, which is a very important and very crucial practice that you should get used to. So that's how you do that one. Okay, so in this question we're told that you use a long rubber band to launch a paper wad straight up, and we're asked to draw a complete motion diagram of the paper wad from the moment the paper wad loses contact with the rubber band until the paper wad reaches its highest point. So this is what I have. I have this axis here, which indicates that the paper wad is moving along. The y-axis is moving up and down, or it's just moving up, but the y-axis is for up and down motion, for vertical motion. And then I have this point here being the point when the paper wad loses contact with the rubber band, right? So when you have this paper wad in the rubber band and you release the rubber band, there's going to be a split few seconds, or a split second, where the paper wad is still in contact with the rubber band, but here is actually where the paper wad is like released and it loses contact with the with the rubber band. So at this point the paper wad is flying vertically through the air. So it's going up and up and up, but you can see through these velocity vectors that it's actually slowing down. And that's because of acceleration due to gravity is constantly acting downward. That's why I tried to draw all these acceleration vectors the same length, because gravity is acting with the same constant force downward. So it's going to slow down the velocity until it reaches its highest point. And if this graph were to continue, you'd actually see the object, the paper wad, start to fall down, and then the velocity vectors are going to point downward, and they're going to get longer again as acceleration due to gravity is making the velocity increase, making it speed up as it hits the ground. You can also see that I labeled this the highest point. I've labeled my acceleration vectors and my velocity vectors. I've condensed the paper wad down into a point, a massless point, so that's the complete motion diagram.
Okay, so in this next question we're asked to determine how many significant figures are in the following values. And our values are 0.05 times 10 to the negative fourth, 7.2 times 10 to the fourth, 0.00340, and 103.00. So in this first one, what we need to remember is that any zeros before a non-sig fig is not a sig fig. So these two are not significant. And if we have a times 10 to the whatever, those don't count as significant either. So these are not significant figures. The only significant figure here is this 5. So the number of sig figs in part A is 1. In B, we have two non-zero numbers, which are always sig figs, and of course these don't count as sig figs, so we have 2. Then in this one, once again, any zeros coming before a non-sig fig is not a sig fig, so these are not significant. But any zero coming after a sig fig is a sig fig. So this is a sig fig, and this 3 and 4 are sig figs. So that's a 3. There's 3 sig figs in part C, and in part D we have. This is a sig fig because it's a non-zero. This 3 is a sig fig because it's non-zero. And the 0 in between them is a sig fig because it comes after a sig fig. And same thing for these 2 zeros after the decimal point. So we get that there's 5 sig figs in part D.
Okay, so in this next question we're asked to convert the following to SI units: 75 inches, 3.45 times 10 to the 60 years, 62 feet per day, and 2.2 times 10 to the 4th miles squared. So this is what I have. So for this first one, you're going to want to convert inches to centimeters, and then centimeters to meters, because that's your SI unit of length. And the key to remember here is that 1 inch is 2.54 centimeters, and if you do that, as well as your centimeters to meters conversion, you're going to get 1.905 meters. Then for the years one, what you're going to want to remember is that the SI unit of time is seconds, so we're going to want to convert years to days, days to hours, hours to minutes, and minutes to seconds. And once you do all that, you get 1.09 times 10 to the 14th seconds. Then for 62 feet per day, like I just said, your SI unit of length is meters, and your SI unit of time is seconds. So I converted from feet to meters first, and then from days to seconds, but you can do it in either order. and you should get 2.19 times 10 to the negative 4th meters per second. And then for 2.2 times 10 to the 4th miles squared, your SI unit of length is meters. But the important thing to remember here is that you want to square everything because it's miles squared. And if you do that, you get 5.70 times 10 to the 10th meters squared. Okay, so in this next question we're asked to perform the following calculations with the correct number of sig figs. And our calculations are 159.31 times 204.6, 5.1125 plus 0.67 plus 3.2, 7.662 minus 7.425, and 16.5 divided by 3.45. Now the important thing to remember here is what you do with sig figs when you multiply and divide versus what you do with sig figs when you add and subtract. When you multiply and divide, you take the least amount of sig figs there are in any given term you're given, term being just one of these sets of numbers, I suppose you could call them. So for example, 159.31 has 5 sig figs and 204.6 has 4 sig figs. So we take the least amount of sig figs in a number, which is 4, and that's how many sig figs our final answer is going to have. With addition and subtraction, it's you take the least amount of sig figs there are after the decimal point, and that's how many sig figs after the decimal point your addition or subtraction is going to have. So here's what I got for this one. So in part A, once again we have 4 sig figs in 204.6 and 5 sig figs in 159.31. So the answer I got when you just straight multiply these is 32,594.826, but you're going to cut it off at the 4th sig fig, and because 4 isn't enough to round that 9 up, we just have to leave it as 32,590. In part B, where we're adding, the least amount of sig figs after the decimal point is 1 sig fig in 3.2. So when we have our final answer, which is just 8.9825, we're going to go 1 sig fig out, and that's going to be our cutoff. But this 8 is enough to round up the 9, and if you round up the 9 on 8.9, what you get is 9.0. Now the same idea is happening in part C. That's just a straight subtraction, and there's 3 sig figs beyond the decimal place in both numbers. So, and once you subtract straight across, you just get 0.237, which is 3 sig figs, so we're fine there. And for part D, it's the same thing. There's 3 sig figs in both numbers, so we divide them, we get this really long number, and cut it off after the 3rd sig fig, and 2 is not enough to round up to 8, so our answer is 4.78. Okay, so in this next question, we're told that a 5.4 centimeter diameter cylinder has a length of 12.5 centimeters, and we're asked to find the centimeters volume in SI units. So this is what I have. The first thing I did was I drew a picture of the cylinder because pictures can help, especially for me, I'm a visual learner. Then I wrote out the formula for volume, which is V equals pi r squared h. And then I found the radius, which is just half of the diameter. If you think about a circle, the diameter is like 2 end points on a circle, and you draw a line through them, then that's the diameter, and it has to go through the center of the circle too. So the radius is just going to be half of that, so that's 5.4 divided by 2, which is 2.7 centimeters, but since they want it in SI units, I went and converted it into meters, so it's 0.027 meters. And then the length, which I took to be the height of the cylinder, was 12.5 centimeters, which I converted to meters and got 0.125 by the same process that I did for the radius. And then so I just plugged those numbers into the formula, and I got that the volume is 2.86 times 10 to the negative 4th meters. Meters cubed, actually, would be the correct way to write that. So that's how you do that one.